Right now, as you watch this video, you're traveling through space at 828,000 kilometers per hour. But here's what nobody told you. You're not just floating through empty void. You're inside a tunnel. A cosmic highway carved by exploding stars millions of years ago, connecting our solar system to distant constellations. And scientists just confirmed it exists. This is the story of the interstellar tunnels, the local hot bubble, and what it means that we've been living inside a cosmic network this entire time. In 2024, astronomers at the Max Planck Institute published findings that confirmed decades of speculation. Using the eRosita X-ray Observatory, part of the Spectrum Röntgen Gamma mission, they mapped channels of hot, low-density plasma stretching from our solar system toward the Centaurus and Canis major constellations. These aren't metaphorical connections. They're actual physical structures. Tunnels of superheated gas, roughly 300 light-years across, that link star systems together like cosmic backroads. Dr. L. Sala, the lead researcher, described temperature differences across these regions that suggest they're open pathways rather than closed bubbles. Published in Astronomy and Astrophysics, this discovery answers questions scientists have been asking since the 1970s. To understand these tunnels, we need to understand where we live. Our solar system sits inside what astronomers call the local hot bubble, a region of space about 300 light-years in diameter, where the gas is significantly hotter and less dense than surrounding areas. Temperature here reaches about 1 million Kelvin. That's hot enough to emit X-rays, which is how eRosita detected it. But here's the fascinating part. We haven't always been here. Our sun drifted into this region relatively recently in cosmic terms, within the last few million years. The timing isn't coincidence. The bubble itself formed from a series of supernova explosions that occurred 10 to 20 million years ago. These stellar deaths released enormous amounts of energy, heating the surrounding gas and pushing it outward, creating this low-density cavity. The walls of this bubble are made of cooler, denser material, the compressed gas pushed aside by those ancient explosions. When a massive star explodes as a supernova, it doesn't just disappear. It releases energy equivalent to the sun's entire lifetime output in a matter of seconds. That energy creates a shockwave that travels through the interstellar medium at thousands of kilometers per second. As multiple supernovas exploded in the same region over millions of years, their shockwaves overlapped and interacted. Where they met, they created boundaries. Where they didn't, they carved channels. Think of it like water erosion, but with plasma and magnetic fields instead of liquid. The tunnels we're detecting now are the remnants of those pathways, corridors where the hot gas can flow with less resistance. The plasma inside these tunnels is roughly 100 times less dense than the surrounding interstellar medium, making them cosmic highways for charged particles, radiation, and magnetic field lines. Here's where it gets truly mind-blowing. The local hot bubble isn't alone. Astronomers have identified similar structures throughout our galaxy: the Loop I bubble, the Eridanus bubble, and others. And the new data suggests they're connected. The tunnels stretching towards Centaurus and Canis Major might link our bubble to these other regions, creating a galaxy-spanning network of hot, low-density channels. This idea was first proposed in the 1970s by researchers who noticed patterns in X-ray emissions, but they lacked the technology to prove it. Now, with eRosita's sensitivity and the combination of old ROSAT data, we can see the connections. This network might explain several cosmic mysteries: how cosmic rays propagate through the galaxy, why certain regions show unusual magnetic field alignments, and how star-forming regions influence each other across vast distances. Understanding these tunnels has practical implications for humanity's future in space. Cosmic rays, high-energy particles that pose radiation risks to astronauts, travel along these channels. Knowing their structure helps us predict radiation environments for future missions. The tunnels also affect how dust and gas move through space, which influences star formation and planetary system development. For interstellar travel concepts, these low-density regions might offer advantages: less resistance for spacecraft, reduced particle collisions, and potentially more stable magnetic field environments. They're natural highways through the galaxy. But there's also a darker consideration. If these tunnels channel cosmic rays efficiently, they might create radiation hotspots that future spacefaring civilizations need to avoid. We've confirmed the tunnels exist, but we're just beginning to understand them. Key questions remain. How stable are these structures over time? Do they evolve as new supernovas occur? Are there tunnels we haven't detected yet, perhaps connecting to even more distant regions? Future X-ray missions with higher sensitivity will map these structures in greater detail. Radio telescopes will trace magnetic field lines through the tunnels. And multi-wavelength observations will reveal how different types of matter and energy flow through them. The discovery also raises philosophical questions. How many other solar systems are connected to this network? Could these tunnels facilitate the spread of life-bearing material between star systems? We're not just mapping space. We're discovering that space has structure, pathways, and connections we never imagined. The interstellar tunnels remind us that space isn't empty. It's a dynamic, structured environment shaped by violent cosmic events over millions of years. We're not isolated in the void. We're part of a connected network of bubbles and channels that spans the galaxy. And we've only just begun to map it. Complex breakthroughs, simple explanations, every day. Subscribe for more deep dives into the cosmos.